Hi all, and welcome to my presentation on Scylla Cloud, the Serverless edition. I'll be talking on Scylla Cloud Serverless, a new important feature coming to Scylla Cloud. We've already released it as a beta just a month or so ago for the trial tier, and we are very excited about it. Today, I wish to share more details about it with you. But let me start by introducing myself. I've only been at Scylla for a few months now, and I can tell you how energized I am with the work we are doing. I've been part of two major releases already, 5.1 on the open source side and 2022.2 on the enterprise side, as well as this initiative, Serverless, which is an exciting journey by itself. I've been working with and contributing to open source for more than 20 years now, and it's always been a great experience. I've moved to working with storage about 10 years ago. I still remember someone advising me against it. Storage is slow moving. Huh. I personally find the challenges with performance and reliability motivating. What's the bee doing here? Well, it's one of my hobbies, taking close-up pictures of bees and butterflies and flowers. This one was taken in the northern part of Israel on a lovely day just a month ago. So what are you going to hear today from me? I'll give you a short introduction, a tour of how it looks like, and how you work with serverless. Then I'll provide a behind-the-scenes overview of its architecture. In between, I'll mention some of the implementation challenges we've had along the way and our design choices. Let's get started. I'd like to begin my introduction with a quick reminder of what Scylla Cloud is, then what is serverless, and we'll move over quickly to a visual tour of the user experience. So let's start with a short recap of what Scylla Cloud is. It is a ScyllaDB offering for customers who do not wish to run Scylla Enterprise by themselves and own the day one and day two operations, and prefer that we manage the clusters according to best practices, monitor their health, provide day two operations such as upgrade or preemptive expansion, and so on. It is currently available in multiple flavors. Specifically, it is running on both Amazon and Google Clouds in multiple regions around the globe. Today, in Sync Cloud, every tenant gets a dedicated set of complete virtual machines for their clusters. We pick them according to our sizing guide, taking into account performance and capacity requirements. When needed, we make adjustments, proactively replace nodes, and if needed, we change the architecture. We deploy more nodes. We do different sizing. Anything that needs to happen, or reactively when a node becomes faulty. We also scale up and scale down regularly based on customer demands. So what is serverless all about? Serverless is a major step we have taken into our next generation architecture, running Scylla clusters on top of Kubernetes infrastructure. Infrastructure component management, such as storage, network, security, monitoring, logging, and more, is handled by Kubernetes and via standard Kubernetes primitives, operators, CRDs, and kube control if needed. There is also a seamless integration with the cloud services. As an example, VPC for networking, instant provisioning for scaling, security features, and so on. As for the core Scylla components themselves, Scylla nodes have been delivered via containers for quite some time, along with other distribution formats, of course, like this RPM and deb packages or MI images. The Scylla Kubernetes operator has matured quickly, gaining more and more day one and day two operations and integration. It is one of the magic ingredients of this effort. Let's take a tour of how the user-facing part of it looks like. Upon logging to Scylla Cloud, you can create a cluster, and right now, serverless is in beta. Let's take a look at how it works. During cluster creation, the flow behind the scenes is that our Scylla Cloud Management software asks the operator to create a full Scylla cluster. It provides it with the input from the user, enriched with the default settings, for example, replication factor, and the cluster is formed, initialized, and eventually launched. Our default, for example, is 3 replicas, each in its own availability zone in a single region. And there we go. We launched our cluster is ready. It is fully deployed and can accept user input. We can now go ahead and proceed to connect to it. Let's proceed to see how the UI looks like for a running cluster. Just a note before that, all the cluster creation flow can also be done via a REST API or a Terraform provider, which of course uses our REST API. So this process can be easily integrated into a customer's automated workflow. Here, we can see the overview of the cluster. We can get some of the data on the running cluster and very basic statistics of operation. From here, we can go to the Connect tab, which we will in a second. We can launch the external monitoring view, which I'll show later, or we can take some actions on the cluster. Let's move to the Connect tab and learn how we connect using CQL to the running cluster. The first step in connecting with the cluster is downloading the connection bundle to the client. The bundle is a simple YAML file containing all the connection details needed for a serverless aware driver to connect to it. Let's take a concrete example, the CQL shell, as an example of how we connect. We have containerized CQL shell, so it will be easier to use. I've copy-pasted the command line from the example in the UI. Let's examine it in details. We call Docker as the container execution engine to launch a container, and we pass to the container a file from the host, the connection bundle we've downloaded earlier. That file is passed as a configuration file to CQL shell. This provides CQL shell all the information it needs to securely connect to the cluster. And voila, we are connected. As I've mentioned earlier, all we had to do is pass the connection bundle file to the various drivers in order to connect to the cluster. This provides a very smooth experience to the user. Here, we can see an example written in Python. I promise you I won't go over it line by line. You can see from this plain example that all we do is construct a cluster object with that aforementioned bundle via the path, and then it simply calls the connect method to connect to it. That's all there is to it. Last user interface element I'd like to show you is the monitoring stack. It's the usual stack of Grafana with Prometheus reading our exported metrics. Notably missing is the node OS level metrics that we used to have in VM or bare metal based clusters, as they are simply irrelevant for serverless. However, we do monitor the Kubernetes nodes and we do collect those metrics in our stack, as our DevOps team watch the Kubernetes node health continuously. Now that we have seen how it looks like, let's do some deep dive into how we've built it. I'll explain the high-level architecture of it in a few slides. I'll be honest, Kubernetes was not designed from the ground up to be running stateful application, and probably at least initially not for high-performance, latency-sensitive applications. So I'll admit it has made steady improvement in both areas. Scylla is a stateful application, a database, requires more processes and steps than a stateless application. As an example, rolling upgrade of the application must be properly coordinated and executed, one node at a time, making sure they're all responsive after upgrade. Pods have a persistent identity, for example. Scylla also has strict requirements for the operating system itself in order to achieve very high performance. CPU scheduling, IO requirements are two specific examples. We also have deployment requirements. We support multiple data centers in different regions, and we use NVMe disk for high performance. As mentioned earlier, ScyllaDB Cloud Management System already supports multiple cloud providers, including Amazon with Scylla AWS account or bring your own account, as well as Google Cloud Platform. So extending it by treating serverless as just another cloud flavor was a natural fit for the architecture for us. We do run multiple Kubernetes clusters. We separate infrastructure services used for management, monitoring, and alerting to a separate Kubernetes cluster than the one that is running the workloads themselves. We deploy the Scylla clusters themselves on Kubernetes worker nodes. The Scylla operator takes care of it in two steps. The first is initialize the new Kubernetes node. if needed and one is not already available. We run a privileged operator that prepares some parts of the node for our own usage. Specifically, in case the Kubernetes node have multiple disks, we set it up in a RAID 0 configuration, format it, and set some OS configuration items. The second step is to run a disk I/O benchmarking software. So we'll know how much IOPS we can squeeze from the local disk. I'll show in details later how we use this information. Now, the Scylla Kubernetes operator using a CRD deploys a complete Scylla cluster. Number of node, size, which is the number of cores, the memory, and of course the disk, the distribution, the replication factor. Specifically, replication factor equals 3 for the time being. It configures and initializes the Scylla nodes and waits for the cluster formation. It installs the Scylla manager agent and configures. It sets up a monitoring stack. Lastly, it deploys a driver proxy, also known as SNI proxy, which I'll discuss later. And we're done. The cluster is ready for use. So what changed? With virtual machine, we have a fixed set of relationship between number of cores, amount of memory, and size of storage each node of a cluster can have. Scaling can be performed either by adding or removing nodes or by replacing nodes with different node types, somewhat heavy operations. Using Kubernetes, we abstract underlying hardware and provide much more flexibility and elasticity. For ease of use, we match CPU and memory resources, but both can scale, and so can the storage dynamically. This means customers no longer need to commit to hardware resources ahead of time. They can scale much more easily and quickly with resources that match their performance and capacity requirements in a granular and efficient manner. Let's discuss in more depth a critical feature that's part of the architecture, tenant isolation. With multiple tenants running side by side on the same physical node, we have to ensure all resources are shared but isolated. Memory and CPU is kind of built into Kubernetes. We set a request and limit on the resource definition, and we schedule them using CPU sets on different vCores, so they don't impact each other. These resources are shared, and it's the more interesting part. Let's look into how it's achieved. First, we have to ensure no customer uses the whole storage or just more than was allocated. For that, use the XFS file system quota feature. We define a quota for each month. To scale, we use the CSI volume expansion API, and it adjusts the quota accordingly and dynamically, of course. CSI, by the way, is the container storage interface. It's a standard API in Kubernetes to handle storage. Quota itself is not enough. Just as important is to ensure there's no noisy neighbor impacts, that different tenants don't use all the IOPS the underlying storage can provide. I will not go right now into the details of how Scylla's IO scheduler works, but if you recall, I mentioned earlier we run a benchmarking software on the underlying storage. From its result, we know how many IOPS we have overall, and we can provision it across tenants relative to the number of vCores each tenant was assigned. So we split the resources overall, all IOPS that we have in per node, into the different tenants. Each tenant gets a slice of it, and its IO scheduler knows to adjust to it. Here's a very preliminary results of our performance test on a small scale system. Just to explain in a high level what the test is, running multiple workloads from multiple clients against multiple tenants running side by side. We measure throughput, operations per second, and tail latency, the famous P99, for all workloads. As you can see, we have two different workloads, OLTP and OLAP, an interactive and a non-interactive workload. The overall plan here was to measure we can run multiple tenants and indeed witnessed three key achievements. The first is tenant isolation. Tenants do not suffer from noisy neighbor impact. The second is there is fairness between evenly set up tenants. Each get their own share of the entire horsepower that the Kubernetes node can deliver. The third is that aggregated, we are close to what this node, had it been a single VM, can deliver. We're still not there, we still have some known gaps, and we're working on those items. Lastly, let's look at how we connect to the cluster. Two important facts that we need to keep in mind that Scylla nodes have no public IP and in fact can change their IP on a pod restart. Therefore, we need a different way than the traditional way to connect. We are using a feature of TLS, the encryption protocol called SNI, which allows the proxy to redirect the connection. The previously mentioned bundle file has the cluster TLS relevant details, as well as the SNI proxy address needed to connect to the cluster. As mentioned earlier, SNI is a TLS protocol feature. It allows you to connect to a specific node behind the TLS endpoint. Initially, it was used to connect to a specific virtual host that may be deployed together with other virtual hosts on a single physical cluster. Scylla is using to redirect traffic to the correct Scylla node it wants to reach. We are still shardware, we still connect to everything in the cluster, but we do it via the SNI proxy. If you wish to know more about our architecture and implementation, and specifically on our Kubernetes operator, I invite you to go to Scylla University and get more information, including some hands-on experience using the operator. With that, I'd like to thank you for listening and encourage you to get in touch with me if you have any questions on serverless, our operator, or Scylla Cloud. Thank you.